after this short introduction, let's just jump into our service model and let's just describe the first very important constituent of the internet service model, which we are going to call the provider-customer or the transit AS-AS relationship. Again, the service model's main use is to reason about the internet topology and the routes that arise on top of this topology. Now, the transit service is one type of very simple contractual service that can exist between two autonomous systems. Basically, the transit service is the simplest way to connect two autonomous systems, or actually to connect one autonomous system through the other autonomous system to the rest of the internet. In the transit service, one autonomous system acts as a service provider, and the other autonomous system acts as a customer. And in this particular contract, the provider is contracted to deliver all the traffic from the customer AS to any host on the internet. So this is the egress service. And the other way around, the provider is contracted also to deliver all the traffic from the internet, this time to the customer AS. So it just the backwards direction, the ingress direction, is also covered by this contract. In response, of course, for the connectivity to the rest of the internet, the customer is charged by a monthly fee based on the rate on the provider customer traffic flowing through the inter-AS link. This particular transit service is very, very similar to the types of services, the type of service which we use when we actually want to route or we want to connect our home network as an individual subscriber to the internet. In this particular case, when I want to connect my home network to the internet, I go to an internet service provider and basically buy transit service from them. Now, the transit service that we are talking about here differs only in the simple factor that the actors in this type of transit service are not individual subscribers and internet service providers, but rather fully fledged autonomous systems, which again in themselves can be highly complex networks on their own. We are going to just use the definitions from someone. It's called Dr. Peering, who is a certain individual who frequently blogs about the internet ecosystem Dr. Peering gives us this definition for what we mean by a transit service. As a transit is basically a business relationship whereby internet service providers, the provider AS actually sells access to the global internet to customer AS. From a high-level perspective, this internet transit is basically nothing else than a pipe in the wall, and a plug in the wall that says internet is this way. So it's very, very similar to the type of service that we use to connect our home network to the rest of the internet. One important fact that we often forget when we use an internet provider service is that whenever I connect my home network to the internet, I need at least one IP address that the rest of the internet can use to actually reach my network. So actually the internet service provider provides me with an IP address. Now, in the particular case of autonomous systems, one single IP address will not be enough, because a customer autonomous system itself may contain lots of hosts and lots of routers, maybe in the thousands, and each of them will need separate routable IP addresses and fixed IP addresses. So in this particular case, what the transit provider actually provides to the customer is an actual IP prefix instead of a single IP address. So addressing in this particular case means that the provider can lease or delegate an address prefix to the customer to assign other IP addresses to customer hosts. From that point, the task of the transit provider is to distribute the routing announcement originated by the customer for this prefix to the rest of the internet. So in the previous example, we've seen that it is basically the announcements, BGP announcements, are the way the customer communicates to the rest of the internet that a particular IP prefix and the IP host number from a particular IP prefix are available in its own network. And the other way around, the routing announcements from the rest of the internet also must be communicated back to the customer's border router. So this is again something that the provider provides in this sense. And of course, the provider needs to transfer all internet to customer traffic and the other way around. So these are the three basic services that the transit provider actually gives to the customer. We are going to just go into a little bit more detail now. Now let's see a couple of ways to enter into a transit relationship between a customer and a transit provider. The simplest way to do that is to connect our customer AS to a single provider AS and buy transit from a single provider to the rest of the internet. This is called single homing. So a single homed AS is essentially an AS that connects to the internet through a single provider AS they're buying transit. We're going to use a simple schematic diagram to reason about these small internet topologies instead of actually describing all the hosts and switches and routers and etc. that make up an AS. We're rather just going to represent each autonomous system by a single graph node. So in this case, the customer AS is a single node in our schematic diagram, and the provider AS with all the hosts and routers and everything, infrastructure in it, is again a single graph node, and the graph link between them shows that there is an actual physical link between at least two border routers between these two ASs. And there is a very important distinction that we are going to make, that whenever the type of business relationship between two autonomous systems is transit, then we are going to show or indicate the direction of the cash flow by an actual arrow. So in this case, the arrow goes from the customer to the provider, showing that it is the customer that pays monthly fee to the provider for providing internet access. There are two very important aspects to describe or to discuss when we're talking about AS-AS business relationships. One is addressing and the other is routing. Addressing again means how the customer acquires an IP prefix that it can use to number its IP host, and routing is how the actual traffic is routed to this customer AS, to and from this customer AS through the infrastructure of the provider. So in this particular example, and what is typical in the internet, is that whenever the provider owns a largish IP prefix, in this particular case, this is 192.168.0.0/16, which recall contains more than 65,000 individual IP addresses. It can actually just take a single subprefix of this prefix. In this example, this is a /24, and provision this particular address for use to the customer, and the customer can use this /24 to actually give out addresses to all the IP hosts and all the IP interfaces within its own network from this provider provisioned IP address range. So most of the time, what we see in single-homed transit provisioning is that the customer gets one of the subnets or the sub prefixes of the provider's network prefix. Why this is very important and this is very useful is that this makes the provisioning of the transit service much simpler than it would be the case, and we are going to see in a couple of slides that other models will require much larger complexity or assume much larger complexity on the part of the autonomous system. What's very important in this case is we've seen that one of the responsibilities of the transit provider is to actually announce to the rest of the internet the IP address range of the customer. So naively, the provider would need to announce that /24 to the rest of the internet, because by the contract between the customer and the provider is actually obligated to do that. But in this particular case, we are of luck because the announcement that by all means the provider generates to cover its own IP address range also covers the customer address range, because this prefix is a subprefix of the provider's address space, and that's why we don't need a separate announcement that would be specific to the customer. The default announcement that generates the provider to cover its own prefix is already enough. If you don't understand this just right now, I'm going to just describe this in a little bit more detail on particular examples. So in this particular case, suppose that provider AS uses the prefix, this previously mentioned /16, and I just want to indicate this to you, that this is a so-called private address space. You might have recognized that. This is a so-called non-routable address space. This is just used in these examples for the sake of completeness, but these are not actual routable IP prefixes on the internet. From this /6, please make sure that you understand that from this /16, the provider AS can hand out exactly 256 different /24 subprefixes to its customers. If you can convince yourself that this is the case, that's cool. If not, then please make the calculation for yourself, because for the rest of this talk and for the rest of this lecture series, it will be super important that you understand IP subnetting. Now, suppose that in this particular example, the customer AS receives the 67/24 from the address range of the provider. Again, please convince yourself that this is indeed a subprefix of this prefix. Okay, and we also assume that the border routers also receive or just fall into a single IP subnet. In this particular case, this is 192.168.6.0/24, and the two particular examples are IP addresses are 1 and 2. So suppose that we are given this example. How does the provider announces the customer's prefix? As we've seen, the provider does not need to announce the customer's prefix separately into the routing system, because its own BGP announcement, which goes for a less specific prefix, a larger prefix that contains the customer prefix range, also covers this subprefix. So the announcements that it generates on its behalf, by anyways, already covers the customer's address range, and that's why we don't need a separate announcement in this case. This will be very important in a couple of slides later when we are going to discuss multi-homing, when this is not the case. How does the provider route the customer's traffic to this network? Recall that any IP traffic that is destined into this IP prefix will enter to R1. How does R1 ensure that a part of this prefix, in particular 67/24, will go to the customer's border router, so R2? What happens here is that we installed a more specific entry into the routing table of R1, or the forwarding table of R1. This is usually called a fib. So we add this particular entry into the fib, which means whenever there is a traffic that enters R1, because it belongs to this prefix, but this also belongs to the customer's address range, then let's just apply this more specific route and route this traffic to the border router of R2, where it will just hopefully arrive to the particular destination. In the downstream direction, we use more specific entries in the routing table to distribute traffic between the customers of this provider AS. In the other direction, so how do we get traffic out from the autonomous system of the customer? We simply can use a default gateway if you know what a default gateway is, this is really cool. If you don't know what default gateway is, it's basically just a prefix that matches every IP address, IPv4 address possible. So it's basically a zero length prefix that matches any IP address, but any other IP prefix that might exist in this fib will be more specific, so will dominate this particular prefix. So this is usually called the gateway of last resort. So what happens here is that R2 will be instructed by this default gateway. If you don't know what to do with this packet because you don't have any specific routes for this particular packet, then just route it to R1. So we actually specify the IP address of the other side, so the other border router, as a next hop in this fib entry. And this will basically just tell R2, whenever you don't know what to do with this packet, just handle it over to R1, because R1 will know how to forward this to the rest of the internet. And basically that's all. So in single homing, the role of the customer is very simple. It does not even need to run OSPF or RIP or anything. It does not even have to exchange routing traffic with the provider like BGP, because by using a single default gateway, it can manage all its connectivity. Let's see the pros and the cons of single homing. Of course, there are lots of advantages, and this all boils down to the minimal configuration and maintenance that we need in the single home customer AS, because there is no need for expert IT staff. There is no need for network engineers there, because just a single default gateway will do the trick. The other nice property of single homing is that by the customer's prefix being aggregatable into the provider's prefix, there usually does not arise a separate customer specific routing table entry in the internet. Again, multi-homing, which we are going to just describe next, is something which is against this rule, and we are going to see the types of problems that this leads to. There are a couple of disadvantages as well. Of course, the provider's network and the access link is a single point of failure, so whenever the provider goes away, connectivity to the rest of the internet just fails, and this means poor resilience. And this can also be pricey, at least when we compare to this the single homing to multi-homing, which we are going to describe next. So we describe that single home connectivity means that we buy transit from just one provider, but if we buy transit from multiple providers at the same time, this is what we call multi-homing. So a multi-homed AS connects to the internet by purchasing transit from more than one provider, and the immediate consequence, the immediate advantage of this types of connectivity is that we get much better resilience, because there is no single point of failure in this particular setup. Of course, the schematic diagram just goes over from single homing plausibly. So in single homing, we used to have just a single arrow. Now we have two arrows connecting the customer to all the provider ASs from which it buys transit from, and of course the direction of the arrows just show the cash flow again. Addressing, however, in multi-homing is much more complex than in single homing. The simplest way to provide prefix from the transit provider to the customer is what is called provider aggregatable addressing. So in this case, the multi-homed AS receives a prefix from one of its providers. Like in this particular case, again, one of the providers have this /16, and again, please convince yourself that this particular prefix is a sub-prefix of providers 1 /16. This is all nice, because in this case, provider 1 will not need to generate a customer-specific announcement to the rest of the internet. But what's going on is that even though the customer's prefix is a sub-prefix of providers 1 prefix, it is not aggregatable to providers 2 prefix, And again, please convince yourself, whenever we have a single /24, then there is only just a single /16 which contains this prefix as a subprefix, so it's physically impossible to have to assign a prefix to the customer that would be aggregatable to both of the to provider ASCs. Necessarily one of the ASCs will not be able to aggregate this prefix into its own prefix range, and therefore it will need to generate a separate announcement to the rest of the internet, which is specific to the customer. And this is bad, because in this case there is no aggregation going on. There will be a specific entry at each of the routing tables, at each of the routers that are connected to the internet that are specific to this customer. Let's see an example again in the same vein as previously. We have this 45/24, which is the subprefix of providers 1 address range, but it is not a subprefix of providers 2 address range, and therefore we see a separate announcement, which essentially means an additional fib entry throughout the internet. And this is one of the reasons of the scalability problems that we nowadays see in the internet interdomain routing system. We've seen that basically a single homing is the basic addressing scheme that we see in single homing is provider aggregatable addressing, but in multi-homing it will definitely be the case that at least one of the providers will not be able to aggregate the customer's prefix to its own larger prefix range. Now, if you take this idea further, it can be very well be the case that the customer uses an address range that is neither the subprefix of providers 1 address range, neither the subprefix of providers 2 of provider 2's address range. In this case, there is no way to aggregate this particular address range to any of the to the provider's address ranges. This addressing model is called provider independent addressing. The prefix of the customer is not aggregatable into any of the address ranges of the providers. The providers both need to generate an announcement for this provider independent address range separately. This will definitely need a separate entry in the fibs throughout the rest of the internet. Let's try to compare maybe provider aggregatable addressing to provider independent addressing. If a customer uses PA address prefix, it is tied to the provider. So wherever I use a provider aggregatable address range, I use that particular prefix that I get from the provider to give IP addresses, to assign IP addresses from to each and every interface and host and network device inside my own AS. I need to configure all the firewalls and the DHCP servers and everything like that with a particular IP address that I get from the providers, which is all nice until I want to switch providers, in which case my access to this address prefix will go away. I will need to go to a different provider and you get a different provider aggregatable address range. So I need to renumber, so reassign all the IP addresses in my own AS, which can be a very, very daunting and very, very pricey thing. So in one way, provider aggregatable addressing establishes a certain bound between the provider and the customer that is very difficult to change. Of course, provider independent addressing does not really have this problem. So PI address range, whenever a customer's address range is independent of any of its transit providers, then it will be very simple to just switch and change transit providers, because it does not go with renumbering. The problem is, of course, that PI addressing puts a huge strain on the routing system, because there will be a separate announcement, separate from both of or all of the customers. A very, very fast example. I don't want to go into too much details. This example is just for you to actually see that this particular addressing model and the multi-homing model raises a couple of non-trivial network management issues. So imagine that in this example we have AS1, it has its own slash 16, which cannot be aggregated neither to provider ones, so AS2s and AS3 provider ASs. Address ranges, again, please spend the moment to convince yourself that this address range is not a subprefix of any of the providers' address ranges. If you manage to convince yourself, then we immediately see that this is a PI addressing model. In this case, of course, we usually want the multi-homed AS to connect to the different provider ASs through different border routers, because if we did it through just one single AS, a single border router, then this would mean a single point of failure. So we usually want to operate a separate border router for one of the providers and separate border router for the other providers. Of course, these transit links also do have their particular IP addresses assigned. So how does the routing table look like in this example? We've seen that the first thing that we see in this routing table is a default gateway. Suppose that in this example, AS1 actually decides that it is AS2 which is its primary provider. So whenever it wants to send the traffic to the rest of the internet, by default it will use AS2, and it will use AS3 as just a last resort when the connectivity to AS2 goes away. This basically means that we need to install a separate default gateway into R1 that will send any traffic for which there is no more specific entry in the routing table towards the border router of AS2. We might also add a different, more specific, which will just route all the IP addresses that are within AS2's network to AS2 itself. This is because we might just want to switch the default provider to this guy, but still we want to route traffic that goes to AS2 to this particular AS. Otherwise, we wouldn't need a separate entry for this, because the default gateway actually covers the same prefix range. And of course, we have a specific entry again for the other for all the IP addresses that are in the IP prefix used by the other, the secondary provider AS3 in this case. But of course, in this case, the next hop is an internal route, because we'll need to use R1, we'll need to use R2 to actually reach AS3, and this creates all sorts of interesting problems where the internal route is provided by the interior gate, the intra-domain routing protocol, and the external route is provided by the inter-domain routing protocol, and these two will need to somehow integrate nicely to get a consistent routing behavior. We are going to just describe or delve into that a little bit more in a couple of lectures later. And of course, we also have a couple of internal routes in our routing table. And that's all. What we see in this example is that multi-homing already raises a couple of strange questions, because the customer AS will need to operate separate border routers to benefit from the higher availability that it gets with multi-homing. But then connectivity through multiple border routers will raise all sorts of different issues, which usually necessitate a dedicated network administration and network management stuff already in the customer AS and the customer organization, even though we've seen that in single homing we didn't need that. And this brings us to the last slide of this lecture, the comparison of multi-homing to single homing. Of course, there are lots of advantages of multi-homing, which is basically all boiled down to the greater availability. We can always switch to the secondary provider if the connection to the primary provider goes away. There's a different thing that is often overlooked in this context, is that whenever we have the choice between two transit providers, we can always play with the cost. So we can always choose the less expensive provider as a primary, and this makes it possible to optimize transit costs and bring down transit costs. So multi-homing puts the customer to a much better negotiation position with its transport providers. Also, we're going to see that the customer also can load balance between the providers, basically share its ingress and egress traffic between multiple providers, which again has all sorts of cool benefits. There are of course disadvantages, and the most of the disadvantages boil down to the complex configuration that maintaining multi-home connectivity requires. Border routers need dynamic routing protocols to do the switchover when primary provider dies, and this can be highly non-trivial. We're going to just see in a couple of lectures later how non-trivial this can be in certain cases. And of course, the larger problem with multi-homing is that the prefix of the multi-homed AS, so the customer AS, must be announced into the internet separately, which means that there will be customer-specific entry in the routing tables of all the routers that are connected to the internet. And this brings us to a couple of very uncool scalability problems.